Hello everyone, this is Dr. Zach. So today in AP Calculus, we're going to differentiate our natural exponential functions, and we're also going to build in a little bit of review for your Unit 3 test. So we're going to jump right in. You know that the derivative of e to the x is e to the x. So let's take a wild guess, and I don't know, isn't the derivative of e to the u equal to e to the u times du dx, or u prime? I bet you're right. So let's give this a try. The derivative of e to the 3x minus 1 is going to be equal to e to the 3x squared minus 1 times 6x. Clean it up. I like the 6x to be written in front of my exponential function. I just think it's easier to read. Now, for example 2, we're looking for horizontal tangent lines. So these are some of those application problems that we keep coming up. Know how to do them for your Unit 3 test. That's why this is also part review. To find horizontal tangent lines, you want to know where your derivative is equal to 0. So let's find a derivative. Product rule. So we have y prime equals first derivative of the second plus our second times the derivative of the first. All right, so since I want to set this equal to 0, I think factoring might be a great idea. I'm going to factor out x and e to the x and be left with x plus 2. Now, as I'm looking at this problem, I see 3 factors, 1, 2, 3. So I know x equals 0 is where a horizontal tangent line occurs, where e to the x equals 0 could be a horizontal tangent line, and where x equals negative 2. I have a horizontal tangent line. Let's explore e to the x equals 0. Remember how to solve these. If you were to log both sides of your equation, because the log and e are inverse functions, you would get x equals the natural log of 0. But wait a minute, the natural log of 0 is not a real number because 0 is not in its domain. So this does not give us a solution. We have 2 horizontal tangent lines, and they occur where x equals 0 and where x equals negative 2. Now be aware, if you're asked to find where the points occur, you will need the x and the y. But in this case, since I'm only asking where, the x's will be sufficient for solutions. Example 3 doesn't look like we're fooling around, does it? So what we're going to be working on for example 3 is determining where f prime is equal to 1. And that, of course, is a quotient rule. So let's find the derivative using your quotient rule. We will have f prime of x is equal to, now we have the bottom, times the derivative of the top. And the derivative of the top is e to the 2x times 2. Don't forget the chain rule. Minus the top times the derivative of the bottom. Now the derivative of the bottom, see where that 1 is? That is outside of the argument. So the derivative of the log of 2x is 1 over 2x times 2. And the derivative of 1 is 0. And this is all over the bottom expression, and it's going to be squared. Okay, but we were told to find f prime at 1. I could simplify, or I could substitute first. Guess which one I'm doing. So now I get the natural log of 2 plus 1 multiplied by 2e minus, okay, what do I have? I have another e to the second power minus 1 multiplied by 1. Whew, that was nice. All divided by my denominator, which is the log of 2 plus 1. Now, there's not a lot you can do to simplify this expression other than distributing that negative value. And if you wanted to distribute the 2e, you could, but I don't see why we need to. So we found a derivative at 1. Okay, here's g of x. We want to sketch g prime of x. It feels like it's been a long time since we've done this. So when you sketch a graph, remember you want to think about where it's flattening out. I see a horizontal tangent line near the -2. So I'm going to make a little chart. Here's my -2. Now, to me, it also looks flat on the left side of the graph, and then it looks like it's going up really fast. It doesn't necessarily look like a vertical asymptote, but it's going up quickly. So let's think about what's going on with our function versus our derivative. Oh, these are g's, g prime of x. So the function on the left side, I'm going to say that it is decreasing until it gets to So it was decreasing until it got to -2, and then it started to increase on the right side of 2. Now, as you also look at it, so we want to find our comparisons. Remember, if your function is decreasing, your derivative is negative. So we have a negative for our derivative. Then we're 0 at -2 because it's horizontal. And then it's positive, but not only just positive, it's really steep. So it's positive and steep on that right-hand side. All right, so positive and steep. Okay, so now let's try to draw this graph. So when I'm drawing, I'm going to first put in my 0, and the 0 is going to occur at -2. There we go. Then I want to be negative, but flat. So flat and negative, and I think that looks flat and negative right there. Flat and negative. Then I want to next become positive and rather steep. So positive and, wait, it kind of looks like the graph we were working with, but isn't that what happens with exponential functions? Yes, it is. So you should be very well aware that that's what's going to happen. Okay, example 5. Let's see what we can do. The number of shares traded in millions on the New York Stock Exchange in 1990 was 36,663. And it was that large amount in 2002. We're going to write an exponential equation to represent the growth. So that's not calculus, guys. That's pre-calculus. We need some sort of function, and that function is y equals a. If we're going to use exponential growth, we're going to use e, and then perhaps bx. That is one way to do it. Now notice I have 2 missing variables, a and b, that I need to find, which, oh, look at that. I have 2 points. Isn't that convenient? So now if I'm going to do this problem, I'm going to make it easier on myself. I'm going to let 1990 be when t equals 0. That's going to make my life so much easier. So if I now have 2 points, I have 0, 36,663. I'm not going to put that extra comma in there. It'll be too confusing. And in 2002, okay, that would be 12 years later. I'm going to use a 12. And then 359,303.73. Unfortunately, it's real data, which makes it ugly. All right, so what we're going to do substitution. When x is 0, your y value is going to be 3663, and that means I would have a e to the 0, but e to the 0 is 1, so now we know our a value. Hey, that wasn't so bad after all. Okay, so next thing we're going to do is figure out the b value if we can. Use our same function. We'll get y equals, we'll have our a, 36663, e to the bx. Do some substitution. We get nasty number equals, oh, let's do the division now. And then we'll have e to the bx. B is missing, and the x is 12. All right, now, this is where your log skills come in. You know that if you take this function and log both sides, yes, I said that, hit it with a log, you end up with the natural log of that nasty number is equal to, what happens with log and e? They cancel out, so you have 12b. And then you divide both sides by 12, and you now know your b value. Okay, so at this point, I think I better go figure it out. So give me a moment. Okay, so you can see that I have determined b, and I have also written the equation that we were looking for. All right. Now, if I want the rate of the number of shares was trading in millions during 2010, I'm looking for y prime. Now, I don't want to use 2010. That would actually be 20. And substitute your derivative, find your derivative, substitute the value in, you are set. So that would be 0.1902 multiplied by 36663 e to the 0.1902 times 20, and you come up with some sort of number. All right, you find it, I'll find it, then we'll both write it down. So as you prepare for your Unit 3 test, make certain that you understand all of your rules for your exponential functions, your algebraic rules, as well as your calculus rules. Make certain that you can apply your chain rule, your product rule, and your quotient rule for all of your exponential and logarithmic functions. And today's practice, make certain you are doing the even questions in that first column again. Don't do too much work, but if you want to do more work, you go right ahead. Have a great day.